Now let us try to take another model here. Okay, we are given that two spheres of radii in the ratio 2:3 have a specific heats in the ratio 3:4. Their densities are in the ratio 4:5. Their water equivalents are in the ratio. The options given are 2:5, 4:5, 8:45, 45:8. Water equivalent is given by W equals to ms, where mass is written as volume into density into S. Volume is given as 4/3 pi r cube d into S. We require the ratio of the water equivalents. So, let me write it as W1 by W2 is equals to R1 by R2 whole cube into D1 by D2 into S1 by S2. Here R stands for the radius, D stands for the density, and S stands for the specific heats. The ratio of radii are given as 2:3, and ratio of densities is given as 4:5, and ratio of specific heats is given as 3:4. Now substituting those values in these places, we get W1 by W2 is equals to R1 by R2 is written as 2:3, that is 2/3 whole cube, into D1 by D2 is given as 4/5, and S1 by S2 is given as 3/4. Okay. Then after that, we can write it as 8 by 27 into 4/5 into 3/4. 3 ones, 3 nines, 4 and 4 gets cancelled off. Now we are getting it as 8 by 9 5 is 45. So we have the ratio as 8:45. 8:45 is our third option. Therefore, the third option is correct there. Now let us take another model here. A man releases 270 kilocalories of heat in 1 hour during a physical exercise. Then the amount of sweat evaporated from his body is. We are given latent heat of water as 540 calorie per gram, and here we are given the options as 0.54 kg, 0.5 kg, 0.27 kg and 0.1 kg. In the given problem, we are given Q is equals to 270 kilocalories, which can be written as 270 into 1000 calories, and we are given the latent heat as 540 calorie per gram, and we want the mass here. So the relation between Q and L is given as Q is equals to ml, where m is given as Q by L. Substituting the value of Q, we get 270 into 1000 divided by the latent heat is given as 540 here. So 271 and 272 times, we are having 1000 by 2, and 1000 by 2 can be given as 500 grams, and 500 grams is nothing but 0.5 kg, and that 0.5 kg is in option number 2. Therefore, our answer is number 2. Okay. Now let us take another model here. A body of mass 2 kg is drawn with a velocity of 2 meter per second on a horizontal table. If the coefficient of kinetic friction is 0.3, calculate the heat produced in 5 seconds. We are given G value as 9.8 meters per second square. The options are 5 calories, 10 calories, 14 calories and 28 calories. In this present problem, the body is drawn with a velocity of 2 meters per second. Velocity of body is v equals to 2 meters per second. This implies velocity is constant, therefore acceleration of the body will be 0, and the work is done due to the frictional force. The frictional force is given by F is equals to mu mg. The value of mu is given as 0.3 and the mass of the body is given as 2 kg and g is given as 9.8. Okay, and the distance travelled by the body is given as velocity into time. The velocity is given as 2 into, and the time is given as 5 seconds. Therefore, 2 into 5, it is given as 10 meters. But we want the work done actually. The work done is given as frictional force into displacement. Both the frictional force as well as the displacement, they are in the same direction. Therefore, theta is taken as 0 degrees, cos 0 is 1. Therefore, we are writing W equals to just F into S. And F is written as 0.3 into 2 into 9.8 into the 10 meters. Then work done is given as, on multiplying all these things, we get the work done as 58.8 joules. All the given values are in SI system, therefore we are getting it as 58.8 joules. But what we require is the amount of heat produced. The amount of heat produced is given as Q is equals to W. So it is written as 58.8 joules in CGS system. Q is equals to W by J. Therefore, 58.8 by 4.2, which gives us 14 calories. Therefore, our option is 3. Now, let us take another model here. Okay, fine. From what height a block of ice must fall into a well so that 1/100th of its mass may be melted? We are given G is equals to 10 meter per second square. And the options we are given are 300 meters, 336 meters, 660 meters and 500 meters. Now, in the problem, we are not given block of ice mass. So, we imagine it as M. Let mass of ice block is, this ice block is at height h. Due to the presence of the block at height h, it possesses some potential energy. The potential energy of the block is, let the quantity of ice melted 1/100 of total mass. Latent heat of ice is given as 80 calories per gram. From Joule's mechanical equivalent of heat, we are given W equals to Q, from which what we can get is mgh is equals to 1/100th of mass of ice block into the latent heat. Let us substitute the values here. M into 9.8 into h is equals to 1/100 into the mass m into latent heat of ice is given as 80 calorie per gram. So, 80 into converting calorie per gram, we get 4200. On simplifying this, we get h is equals to 336 meters and our option is second here. Now, let us see another model here. Two spheres A and B of masses in the ratio 1:2. Specific heats are in the ratio 2:3. They fall from a heights h1 and h2. On reaching the ground, the increase in temperatures are the same, then the ratio of heights h1 by h2 is given as. We are given the options as 3:2, 9:4, 2:3 and 4:9. Now let us see the problem there. Okay. Here we are given ratio of masses as m1:m2 is equals to 1:2. Ratio of specific heats is given as 2:3. And we want the ratio of heights. Here the problem is related to the Joule's mechanical equivalent of heat, which says that W equals to Q. W is given as mgh and Q is given as ms delta theta. In this case, mass gets cancelled off. G is a constant, and in the problem it is given that delta theta is the same. So, H is proportional to S. I can write it as H1 by H2 is equals to S1 by S2, and ratio of specific heats is given as 2/3. So, we get the option as the third one. Now, let us see another model here. 0.1 kg steel ball falls from a height of 10 meters and bounces to a height of 7 meters. Then the rise in temperature of the ball is, we are given specific heat of steel ball as 0.1 kilocalorie per kg per degree Celsius. And the options given are 0.05 degrees Celsius, 0.064 degrees Celsius, 0.06 degrees Celsius and 0.07 degree Celsius. Okay. It is also a problem relating to the Joule's mechanical equivalent of heat. So, given is W equals to Q. Here, work done is change in potential energy. PE1 minus PE2. This is the change in potential energy. Initial potential energy is mgh1. Final potential energy is mgh2. The difference of them is given as mg into h1 minus h2. This change in potential energy is converted into the heat. So, heat is given as ms delta theta. Okay. On equating both of them, we get mg into h1 minus h2 is equals to ms delta theta. M gets cancelled off and delta theta, the required one in the problem, is given as delta theta equal to g into h1 minus h2 by s. G is given as 9.8 and difference in heights h1 minus h2 is given as 10 minus 7 divided by the specific heat 0.1 into 1000 into calorie can be converted as 4.2 joules. Okay, and after completing the process, we get the rise in temperature as 0.07 degrees Celsius, which is our fourth option. Now let us see another model here. Okay, fine. 2 kilowatt drill machine is used to bore a hole in an aluminum block of mass 20 kg in 21 minutes. If 60% of the power of the drill is wasted and remaining power is used to heat the block, the rise in temperature of the block is, we are given specific heat of aluminum as 200 calorie per kg per Kelvin. And the options given are 30 degrees Celsius, 60 degrees Celsius, 90 degrees Celsius and 120 degrees Celsius. Here in the problem, we are given 2 kilowatt drill machine. In the sense, power of the machine is given for us. Power is given as P equals to 2 kilowatts, which is nothing but 2000 watts. And it is used for how much time is 21 minutes. The time is given as 21 minutes here. So 21 into 60 seconds it is. Okay. By multiplying power with time, we get the work done. So work done equals to power into time. So 2000 into 21 into 60 joules is the work done. But out of this work done, how much is wasted? 60% is wasted. Then efficiency of the engine is just 40%. In that case, the efficient work done is W into efficiency. It is given as 2000 into 21 into 60 into 40%. This is utilized in raising the temperature of the block. So I can write it as W into efficiency is equals to the quantity of heat developed in the block. So 2000 into 21 into 60 into 40 by 100 is equals to, heat is given as M into S into delta theta, where M is given as 20 kg and S is given as 200 calorie. Calorie can be written as 4.2. Okay. So 200 into 4.2 joule per kg per Kelvin, the conversion part, and the rise in temperature I am writing it as delta theta itself. On simplifying this entire thing, we get delta theta as 60 degrees Celsius. And our option is the second one. Now let us see another model here. A steel drilling is making 180 RPM, here RPM in the sense rotations per minute, under a constant couple of 5 Newton meter, here couple is given for us. It drills a hole in 7 seconds in a metal block of mass 0.6 kg. If its specific heat is 0.1 CGS unit, we are given specific heat in CGS units. Rise in temperature of the block is, okay, and the options given are 1.3 degrees Celsius, 2.6 degrees Celsius, 5.2 degrees Celsius and 3.9 degrees Celsius. Okay. In this problem, again, we are having the relation between work and heat, that is Joule's mechanical equivalent of heat. Here, Q is equals to W. But what actually we require is regarding the work. Work is given as power into time. And power in terms of couple is given as tau omega into T, where tau is the couple or torque acting on the block. It is given as 5 Newton meter. And omega is the angular velocity or angular frequency, we can say. Here omega is given as 2 pi f into the time here given as 7 seconds. So 5 into 2 into 22 by 7 into the frequency. For frequency we are given the information as 180 RPM. Here rotations per minute is converted into rotations per second. For that purpose, we divide the RPM with 60. So 180 by 60 into 7 it is. 7 gets cancelled off and 60 3s are we are getting, and we remain with 5 2s are 10, 3s are 30. 30 into 22 is the work done. But now regarding the heat is given as ms delta theta. Mass is given as 0.6 and specific heat is given as 0.1 CGS unit. 1 CGS unit is given as 4200, okay, fine, times and into delta theta. Substituting both of them in the first equation, what we are getting is 0.6 into 0.1 into 4200 into delta theta is equals to 30 into 22. On simplifying, we get delta theta as 2.6 degrees Celsius, which is our second option. Now let us take a model, a little change one. Okay, up till now we were doing the problems on Joule's mechanical equivalent of heat, that is W equals to Q in SI and W equals to JQ in CGS. Right now we are considering a problem on external work done. Okay, fine. See, we are given a problem here as considering 1 gram of water of volume 1 cubic centimeters becomes 1681 cubic centimeters of steam when boiled at 1 atmospheric pressure. What is the external work done? 1 atmospheric pressure is given as 10 to the power of 5 pascals and the options given are 168 joules, 268 joules, 368 joules and 468 joules. Imagine a container in this manner with a frictionless movable piston. It is having 1 gram of water whose volume is given as 1 cubic centimeter, and then heat is supplied to it. Heat is supplied to the system. When heat is supplied to the system, okay, the gas expands and the piston moves upwards. The piston is moving upwards. As the gas is expanding, the piston is moving upwards. There is a change in volume. Final volume is V2, initial volume is V1, then we are having V2 minus V1 is equals to dV. The atmospheric pressure in the container is given as P equals to 1 atm, which is equal to 10 to the power of 5 pascals. Is it clear? Okay, fine. Now, what we are having is the external work done. External work done dW equals to force into displacement, that is dW equals to F into ds. Now, multiply and divide by the area, we get F by area into A into ds. Force per unit area is given as pressure and area into ds or dx is given as dV. Okay, pressure is given as 10 to the power of 5 pascals and change in volume is given as okay, we are having 1681 cubic centimeters minus 1 cubic centimeters, okay, and converting 1 cubic centimeter into meters, what we are having is 10 to the power of minus 6 meters, okay, and we get 1680 into 10 to the power of minus 1, which is 168 joules, and the option is the first one. Now, let us consider another model here in which we are given 5 moles of oxygen is heated at constant volume from 10 degrees Celsius to 20 degrees Celsius. What will be the change in internal energy of the gas in calories? For gas, we are given Cp is equal to 7 calorie per mole per degree Celsius and R equal to 2 calorie per mole per degree Celsius. As we have seen in the problem, we are having internal energy. Now, let us try to understand what is internal energy. Internal energy is given as the energy possessed by a system due to molecular motion and molecular configuration, okay, and it is given as internal potential energy plus internal kinetic energy. Actually, the internal energy does not depend on the pressure and volume, but it depends upon the temperature. Increase in temperature increases the internal energy and decrease in temperature decreases the internal energy. If temperature is constant, then change in internal energy will be 0. At constant volume, the external work done is dW equals to 0. From first law of thermodynamics, we have got dq is equals to du plus dw. As dw is 0, dq equals to du. Now, dq is given as nCV dt. From Mayer's hypothesis, Cv can be written as Cp minus R. On substituting this value in this equation, we get dq is equals to n Cp minus R into dt. Therefore, we are getting du is equals to n into Cp minus R into dt. Now, the n value is given as 5. 5 into 5 into 10, which is 250 joules. Now, let us see another model here. Okay, fine. 294 joules of heat required to raise the temperature of 2 moles of an ideal gas at constant pressure from 30 degrees Celsius to 35 degrees Celsius. The amount of heat required to raise the temperature of the same gas through the same range of temperature at constant volume is, okay, we are given R equal to 8.3 joule per mole per Kelvin, and the options given are 126 joules, 210 joules, 294 joules and 378 joules. Okay, fine. At first, let us try to understand the problem regarding the constant pressure. We know very well that the specific heat at constant pressure Cp is given as 1 by n dq by dt. Okay, and dq is given as n Cp dt. dq is given as what, Nana? It is given as n Cp dt. In this, we substitute the dq value 294 and number of moles n is equals to 2 into Cp into the change in temperature is 5. So, we get Cp is equals to 294 by 2 5s are 10 in the denominator. We get it as 29.4 actually. The value of Cp is obtained as 29.4 and the value of R is given as 8.3. From Mayer's hypothesis, we have got Cp minus Cv is equals to R and Cv is given as Cp minus R, so that 29.4 minus 8.3, which we get it as 21.1 actually. Now, we know Cv is equals to 1 by n dq by dt. So, dq is equals to n Cv dt. N is actually given as 2 and Cv we have obtained it as 21.1 and we are asked for same range of temperature. So, 35 minus 30 is given as 5. We get 211 nearly. It is taken as 210 joules. Our option is second one. Now, let us see another model here. Find the change in internal energy of the system which absorbs 2 kilocalories of heat and at the same time it does 500 joules of work, and we are given the J value as 4.2 joule per calorie. Okay, and the options given are 9000 joules, 8000 joules, 7900 joules and 7500 joules. As the problem is relating with internal energy, heat and work done, it relates to first law of thermodynamics. What the first law of thermodynamics says? It says that if heat is supplied to a system which is capable of doing work, then quantity of heat absorbed by the system will be equal to the sum of external work and increase in internal energy. Let us say now dq be the heat supplied and du be the increase in internal energy and dw is the external work done. From the statement, we have dq is equals to du plus dw. The sign convention for the statement is heat given to a system is taken as positive, heat given by a system is taken as negative, work done by the system is positive, work done on a system is negative, increase in temperature relates change in internal energy as positive, decrease in temperature relates the change in internal energy as negative. Okay. In the problem, we are given dq is equals to 2 kilocalories, which I can write as 2 into 1000 into 4.2, which is equals to 8.4 into 1000, nothing but 8400 joules. And the external work done is dW equals to 500 joules. Okay. du equals to dq minus dw. dq is given as 8400 minus dw is given as 500. So, we will be getting it as 7900 joules, which is our third option. Okay, fine. Now, let us see a model on change in internal energy. The problem is given as, what is the change in internal energy per gram of air if 5 grams of air is heated from 0 degrees Celsius to 5 degrees Celsius at constant volume by adding 150 calories of heat? All the units that are given are in CGS. Even the options given are 10 calorie per gram, 20 calorie per gram, 30 calorie per gram, 40 calorie per gram are also in CGS units. So, there is no change of units here. There is no change of units here actually. Okay, fine. And now, what we do is we consider first law of thermodynamics. What it says is dq is equals to du plus dw. At constant volume, dw equals to 0. It implies dq is equals to du. dq can be written as 𝗀𝐶𝑉 dt. So, du is equals to 𝗀𝐶𝑉 dt. Now, the formula contains the n moles actually. We need it in grams. So, we can write the same formula as du is equals to 𝗀𝐶𝑉 dt. m is given as 5 grams and Cv is given as 150, whereas the change in temperature is given as 5 minus 0, 5. So, that we are having, okay, 5 is 25, 25 into 150 is actually the change in internal energy, but we require per gram. So, du by m can be given as 25 into 150 by 5 grams. We are getting it as now let us try to understand about the change in internal energy in the form of a problem. Okay, the problem is given as, what is the change in internal energy per gram of air if 15 grams of air is heated from 0 degrees Celsius to 5 degrees Celsius at constant volume by adding 150 calories of heat? And we are given the options as 10 calorie per gram, 20 calorie per gram, 30 calorie per gram and 40 calorie per gram. Actually, in this problem, all the units are in CGS. So, there is no requirement of converting of the units. Okay, but from first law of thermodynamics, we have got dq is equals to du plus dw. At constant volume, okay, the work done will be 0. Therefore, dw equals to 0. So, we get dq equals to du. Whereas, dq is given as 150 calories. So, du becomes 150 calories. But in the problem, we want change in internal energy per gram actually. So, du by m we consider. So, du is given as 150 per gram. So, by 15 we get 10 calorie per gram, which is our first option. Okay. Now, let us take another model here. Okay. It says that a system is taken along the path A, B, C, A as shown in the figure. Okay. The heat released by the system in joules is first option 300 calories, second option 100 calories, third option 150 calories, fourth option 200 calories. Okay. Here we are given a graph. In the graph, we are going from A to B and we are going from B to C, and we are going from C to A. So it is a cyclic process. Okay. In the cyclic process, okay, the work done is given as the area under the graph. Okay, fine. In this case, we are given pressure on y-axis and volume on x-axis. It is an indicator diagram actually. Okay, the change in volume is 1 liter to 3 liters. It indicates 2 liters, and 1 liter equal to 10 to the power of minus 3 cubic meters. So I can write this as 2 into 10 to the power of minus 3 cubic meters. And here the change in pressure is given as from 1 atmosphere to 2 atmospheres, and an atmosphere is given as 10 to the power of 5 pascals. So the change in pressure is given as 1 into 10 to the power of 5 pascals. The area under the graph dW equals to half into base into height. Half into base is given as 2 into 10 to the power of minus 3, whereas height is given as 1 into 10 to the power of 5 pascals. So from which we get 2 into 100 by 2, which is 200 by 2, given as 100. The work done is 100 joules. In a cyclic process, the internal energy remains constant. So change in internal energy equals to 0. From first law of thermodynamics, we have got dq is equals to du plus dw. Put dw is equals to 100 joules and du equals to 0. Then we have dq is equals to 0 plus 100 joules. So dq is given as 100 joules. So the heat released by the system is given as 100 joules, which is second option. Now let us take another model on the graph itself. Okay. A given mass of a gas expands from the state A to state B by 3 paths, 1, 2 and 3, as shown in the figure. If W1, W2, W3 respectively be the work done by the gas along the 3 paths, then the options are W1 greater than W2 greater than W3, W1 less than W2 less than W3, W1 equal to W2 equal to W3, and the last option is W1 less than W2 and W1 less than W3. Okay. In the given graph, volume is taken on x-axis and pressure is taken on y-axis. This kind of graph is called as indicator diagram. In the indicator diagram, okay, the graph close to origin will have least value and the graph away from the origin will have maximum value. So according to that condition, okay, the first one will have least value and the third one will have maximum value and the second one will have in between value. According to that, work done W1 should be less than W2 less than W3. It is the second option in the problem. Now let us see another model. Okay, fine. 1 mole of oxygen gas having a volume equal to 22.4 liters at 0 degrees Celsius and 1 atmospheric pressure is compressed isothermally so that its volume reduces to 11.2 liters. The work done in this process is, and the options given are 1672.5 joules, 1728 joules, minus 1728 joules, minus 1572.5 joules. Okay. In the problem, we have seen a word called isothermally. It means it is a isothermal process. It is one of the thermodynamic process. In this process, pressure and volume change at constant temperature. In this process, pressure and volume change at a constant temperature. As you have said, temperature is constant, dt equals to 0. And in this process, internal energy does not change. So internal energy remains constant. So du equals to 0. From your first law of thermodynamics, as du equal to 0, we have dw equals to dq. It is a slow process and the work done is given as PdV. Boyle's law holds good. It means PV equal to constant and the work done is given by the formula W equals to 2.303 nRT log V2 by V1 to base 10. Okay. And now here N is given as 1 mole. R is given as 8.3. Temperature is given as 0 degrees Celsius. It means 273 Kelvin. Initial volume V1 is 22.4 liters. Final volume V2 is 11.2 liters. On substituting all those values, the work done is given as 2.303 into 1 into 8.3 into 273 into log 11.2 by 22.4 to base 10. On simplifying this, we get work done as minus 1572.5 joules. Now let us take another model here. A monoatomic gas having gamma equal to 5/3 is suddenly compressed to 1/8 of its original volume adiabatically. The pressure of gas will change to, options given are 24/5, 8, 40/3 and the last option is given as 32 times the initial value. Okay, fine. In the problem, we come across a word called adiabatically. It means adiabatic process. It is a process in which pressure, volume and temperature change at constant heat is called adiabatic process. Here in the process, heat remains constant. Q is equals to K. dQ is equals to dK is equal to 0. And from first law of thermodynamics, we have du plus dW equals to 0, dW equals to minus du. Okay. The work is done at the cost of internal energy. It is a sudden quick process and in this process, Boyle's law does not hold good and PV power gamma equals to constant. The work done in this process is given as W equals to NR by gamma minus 1 into T1 minus T2. Slope of adiabatic curve is given as gamma delta P by delta V is equals to minus gamma P by V. And now, when you come to the problem side, what we are having is suddenly compressed 1/8 of its original volume. It means V2 is equals to 1/8 times of V1. So, V2 by V1 is equals to 1/8 and we are given gamma as 5/3. Now, from the law itself, we have got PV power gamma equals to constant. It implies P1 by P2 is equals to V2 by V1 whole to the power of gamma. This we can write as P1 by P2 is equals to 1/8 V1 by V1 whole to the power of gamma. So, P1 by P2 is equals to 1/2 cube whole to the power of 5/3. P1 by P2 is equals to 1/2 to the power of 5. So, P2 is 2 power 5 times of P1, okay, which is 32 times of initial pressure. So, it is our fourth option. Now, let us try to understand about another two processes which are isochoric process and isobaric process. In isochoric process, the volume of the system remains constant. As volume remains constant, change in volume dV equals to 0, so that PdV equal to 0 and dW equal to 0. Therefore, we are having from first of thermodynamics as dQ is equals to du. In this, Gay-Lussac's law is obeyed and in the graph we are having a straight line which represents volume remains constant. Now, in the case of isobaric process, the pressure remains constant. As pressure is remaining constant, we are having dQ equals to du plus dW and we can use Cp minus Cv equals to R. Pressure is constant in the graph. Now let us take another model on adiabatic process. Okay, a gas at NTP is suddenly compressed to 1 by n of its original volume. Gamma is given as 3/2. If final pressure is 8 atmospheres, then the value of n equals 2. Okay, fine. Now here sudden compression comes under adiabatic process. In adiabatic process we have PV power gamma equal to constant. Okay, fine. Then in that case we have P1 by P2 is equals to V2 by V1 whole to the power of gamma. Okay, P1 by P2 can be written as initial pressure is 1 atmosphere and final pressure is 8 atmosphere. So 1 by 8 equals 2. Okay, V1 is V1 itself and V2 is given as 1 by n times of V1. On writing it, we have got 1 by 8 is equals to 1 by n whole to the power of gamma is given as 3/2. Okay, 1 by 2 cube is equals to 1 by n whole to the power of 3/2. Cube rooting on both sides. We have 1 by 2 is equals to 1 by n whole to the power of half. Squaring on both sides we get 1 by 2 square equals to 1 by n and n is given as 4, which is option number 1. Now let us try to understand regarding the degrees of freedom. The number of independent variables that must be known to describe the state or position of the system completely is called degrees of freedom. Relation between degrees of freedom and the ratio of specific heats is given as gamma equals to F plus 2 by F. Let us try to understand about the nature of gas and the values of Cp and Cv and the value of gamma here. Let us say the nature of gas is monoatomic gas and the second one is diatomic gas and the third one is polyatomic gas. In the case of monoatomic gas, the degrees of freedom is 3 and gamma value is given as 5/3, Cp value is given as 5r/2, Cv value is given as 3r/2. In the case of diatomic gas, degrees of freedom is 5, gamma value is given as 7/5, Cp value is given as 7r/2, Cv value is given as 5r/2. In the case of polyatomic gas, degrees of freedom is given as 6, gamma is given as 4/3, Cp is given as 8r/2 which is 4r, Cv is given as 6r/2 which is 3r. Okay, note just concern. Now let us try to understand about molar equivalent mass m. Let us consider a gas having n1 moles with molar mass as m1 and a gas 2 as n2 moles with molar mass m2, and these two gases are in a container and they are in the mixture form. In such case, molar equivalent mass is given by capital M is equals to n1 m1 plus n2 m2 by n1 plus n2. Now let us try to understand about ratio of specific heats of mixture of gases. Let us consider a mixture of gas having gas 1 and gas 2. Gas 1 is having number of moles n1 and ratio of specific heats as gamma 1. Its internal energy is U1, change in internal energy may be du1. Similarly, we are having gas 2 with number of moles n2 and ratio of specific heats gamma 2 with internal energy U2 and change in internal energy as du2. Okay, when these two gases are in a container in the form of mixture, then net internal energy can be given as UV is equals to U1 plus U2. The change in internal energy is given as du equals to du1 plus du2, but we know very well that change in internal energy is given as NCV dt. So NCV dt is equals to N1 CV1 dt plus N2 CV2 dt. All of them are having same change in temperature, so it can be avoided. We can obtain it as N1 plus N2 into CV is equals to N1 CV1 plus N2 CV2. CV is given as N1 CV1 plus N2 CV2 by N1 plus N2. Now, we require regarding CP, but we know CP minus CV equals to R implies CP is equal to R plus CV, R plus N1 CV1 plus N2 CV2 by N1 plus N2. On simplifying, we get N1 CP1 plus N2 CP2 by N1 plus N2. CV is equals to N1 CV1 plus N2 CV2 by N. This we can write as NCV is equals to N1 CV1 plus N2 CV2. CV is given as R by gamma minus 1. C1 is given as R by gamma 1 minus 1. CV2 is given as R by gamma 2 minus 1. Okay. So, we have got N by gamma minus 1 equals to N1 by gamma 1 minus 1 plus N2 by gamma 2 minus 1. Now, let us see a model. For an inert gas, gamma is given as 5 by 3 and R value is given as 2 calories per mole per Kelvin. Okay? Then the values of Cp and Cv are dash and dash. Okay, fine. Now, we know very well that Cp minus Cv equals to R. Divide both sides by Cv. Cp by Cv is equals to Cp by Cv minus Cv by Cv is equals to R by Cv. Gamma minus 1 equal to R by Cv, where Cv is given as R by gamma minus 1, as Cp is equals to R plus Cv, we can write it as gamma R by gamma minus 1. Now, substitute the values in this. What we get is Cv is equals to R by gamma minus 1. R is given as 2, gamma is given as 5 by 3 minus 1. What we get is 2 by 5 minus 3 by 3, and we get it as 2 by 2 by 3, which is nothing but 3. Now, similarly, Cp is equals to gamma R by gamma minus 1. Okay. Now, 5 by 3 into 2 by 5 by 3 minus 1. Okay. So, what we can get here is 5 into 2 by 3 divided by 2 by 3. 3 gets cancelled off and 2 gets cancelled off. We are remaining with 5. So, Cv value is 3 and Cp value is 5. Now, let us take a problem on mixture of gases. A gas, retake the problem completely once again. Okay. Now, let us understand regarding the mixture of gases there. A gas mixture consists of 4 grams of helium and 32 grams of oxygen. Then the ratio of specific heats of mixture is, options given are 1 by 2, 5 by 2, 7 by 2 and 7 by 5. Okay. For monoatomic gas, gamma is given as 5 by 3 and for diatomic gas, gamma is given as 7 by 5. Number of moles are 4 by 4 equals to 1 and for oxygen it is given as 32 by 30 equals to 1. Okay. And from the formula we are having N1 plus N2 by gamma equal to N1 by gamma 1 minus 1 plus N2 by gamma 2 minus 1. On substituting the values, we are having 1 plus 1 by gamma equals to 1 by 5 by 3 minus 1 plus 1 by 7 by 5 minus 1, and we are having 2 by gamma equals to 3 by 2 plus 5 by 2, okay, and where we are having 2 by gamma equal to 8 by 2, okay, and 2 by gamma equal to 4, gamma equal to 2 by 4, and it is given as 1 by 2, okay. Now let us consider a problem. Certain quantity of heat is applied to a monoatomic gas which expands at constant pressure. The percentage of heat that goes into work done is, okay, the options given are 80%, 20%, 60% and 40%. Okay, and we are asked to find out dW by dQ, which is given as 1 minus 1 by gamma. For monoatomic gas, gamma is given as 5 by 3. So, 1 minus 1 by 5 by 3, 1 minus 3 by 5, it is given as 5 minus 3 by 5, which is nothing but 2 by 5, and 2 by 5 is 0.4, multiplying by 100 we get 40%, and the option number is 4. Okay. In the same model, the fraction of heat that goes as internal energy is du by dq, which is given as 1 by gamma, 1 by 5 by 3, which is given as 3 by 5. It is equal to 0.6, and the result will be 60% on multiplying with 100, and the option will be 3 for this. Let us take another different model. An engine takes in a compressed steam at 127 degrees Celsius and rejects it at 47 degrees Celsius. The efficiency of the engine is. This kind of model usually comes under Carnot cycle, okay, in which efficiency is given as eta is equals to W by the quantity of heat supplied. W is given as Q1 minus Q2, and quantity of heat supplied is given as Q1, okay, and from this we can get it as 1 minus Q by Q2 by Q1, okay. Instead of Q2 and Q1 we can write as 1 minus T2 by T1, okay, which is equals to 1 minus, the rejected heat is 47 degrees Celsius, okay, 273 plus 47 divided by T1 is given as 273 plus 127, so that 1 minus, okay, we get it as 320, and here we get it as 400. So, 400 minus 320 by 400, which is equals to 80 by 400, which is nothing but 1 by 5, 0.2, so it is 20%. And the option is third one. An engine has an efficiency of 1 by 6 when temperature of sink is reduced by 62 degrees Celsius. Its efficiency is doubled. Temperature of source and sink are dash and dash. The options given are 99 and 37, 124 and 62, 37 and 99. Last one is 62 and 124. We know very well that efficiency is given by 1 minus T2 by T1. Okay, and in the first case we are given efficiency as 1 by 6. 1 by 6 is equals to 1 minus T2 by T1. From this what we can get is T2 by T1 is equals to 1 minus 1 by 6, which is 5 by 6. So, T2 by T1 is 5 by 6. Let us say it as first equation. Okay. And now, next. What he says is when the temperature of sink is reduced by 62 degrees Celsius. Remember, the change in Celsius is same as change in Kelvin scale. Therefore, same number exists even in the change of Kelvin scale. So, we can write it as 2 by 6, because the efficiency gets doubled, is equals to 1 minus T2 minus 62 by T1. So, what we are having is 1 minus T2 by T1 minus 62 by T1 implies 2 by 6 is equals to 1 minus T2 by T1 is given as 5 by 6 minus 62 by T1. Okay, we are having it as 1 by 6. So, 2 by 6 minus 1 by 6 is equals to minus 62 by T1, from which we can get it as 1 by 6 is equals to 62 by T1, okay, and T1 is equals to 372. If you can subtract 273 from that, 372 minus 273, which we can get it as 9, and here we are having 16 minus 7 is again 9, we are having it as 99 degree Celsius. So the source temperature is given as 99 degrees Celsius. It may be the first option side, okay. And now T2 by 99 is equals to 5 by 6. So we are having T2 is equals to 5 by 6 into 99, 33 by 2. So 5 by 2 into 33, okay. 165 by 2 we are having, which is 8. Retake from here onwards. T2 by 372 is equals to 5 by 6. T2 is equals to 5 by 6 into 372. 6 ones, 6 6 are 36, 6 2s are 12, 62 into 5, 10, okay, 31, 310. 310 minus 273, which we can get it as a, okay, 10 minus 3 is 7, and we are having 37 degrees Celsius. So therefore the temperatures are 99 degrees Celsius and 37 degrees Celsius, which is our first option.